Welcome. My name is Peric, and I'm a researcher at Hamburg University of Technology at the Institute for Fluid Dynamics and Ship Theory under Professor Moustafa Abdel-Maksoud, who is also the co-author of this presentation. And I will be talking about how to do complex 3D flow simulations with nonlinear free surface waves. And the problem here is that we want to reduce undesired wave reflections at the domain boundaries. For this, we can use, for example, forcing zones. Forcing zones are approaches that introduce source terms in the governing equations to gradually force the flow towards a prescribed solution. This could be, for example, to force the flow towards the calm surface solution. The forcing zone is here shown in shaded gray, or to force the flow towards the far-field wave solution so that we generate the desired wave, but wave reflections happening at bodies within the domain are minimized and gradually faded out. Examples of such approaches are sponge layers, absorbing layers, damping zones, or relaxation zones, but they can all be traced back as special cases of the generic forcing zone formulation. The main advantage of forcing zones is that one can use them to simultaneously generate the desired wave and damp undesired wave reflections. However, the forcing function contains case-dependent parameters. And if these parameters are not set up correctly, then the approach does not work and one gets a lot of wave reflection. So these case-dependent parameters require tuning. So let's have a look at one example. We have a wave traveling to the right into a forcing zone, and we want to force fluid velocity u to some reference solution, for example, to 0 to damp the wave. Then you see here the Navier-Stokes equations, the momentum conservation equation in gray. And we add at the right-hand side a source term, qi, which is a function of the difference between our velocity and our reference velocity. And the three case-dependent parameters are in here. The blending function, b, it takes values from 0 to 1 and gradually increases the source term magnitude within the zone. The zone thickness, this is typically in the order of 1 or 2 wavelengths. And the forcing strength, gamma, this is the magnitude of the source term. So gamma 0 means the source term is turned off. And we've shown in a previous publication 4 years ago that the default values for these parameters can produce large errors. And the problem is therefore how to find their optimum values for complex 3D flow simulations so that the waves are properly damped. And to look at the solution, let's look at how such a simulation might look. We have here a pontoon subjected to regular free surface waves. The pontoon is strongly wave reflecting, and it's shown in gray. And the forcing zones are attached near all vertical domain boundaries, shown here shaded gray. And we use different types of forcing here. For example, on the left-hand boundary where the waves are generated, we force towards the far-field wave solution to generate the desired waves and minimize wave reflections. And these waves travel towards the outlet boundary where they are partially damped in a forcing zone, and if the setting is not correct, partially reflected. Here at the outlet, the solution is forced towards the calm surface solution to damp the waves. And at the domain sides, we use the special forcing zone that lets the generated waves pass through undisturbed and damps all waves that are reflected from the body within the domain. Typically, when talking about wave reflection, we talk about the wave reflection coefficient, which is the height of the reflected wave divided by the height of the generated wave. But this is difficult to calculate for such a setting because not only are waves reflected at the outlet, but also the body within the domain reflects waves towards all domain sides. And these are, again, partially absorbed and partially reflected back into the domain from the forcing zones. So, and the idea is to split this in two problems to simplify the problem. First, we have the generation of regular waves, regular long-crested waves here that are generated at the left boundary, travel to the right, and in a forcing zone, shaded gray again, they are damped and partially reflected back. And for this flow problem, we have an analytical solution that we derived 2 years ago and we can thus very well predict the actual reflection coefficient for this problem. The analytical approach is called in the following 1D theory, meaning that it's a wave traveling in one direction, so long-crested waves. Of course, the solution itself is three-dimensional. So this we know, and the new part in this presentation will be that we consider the waves radiated at the body within the domain. With the following problem, we have forcing zones near all vertical domain boundaries in the squared domain to damp the waves. And in the center of the domain, the black dot, we have a source that generates circular waves, and these are partially absorbed at the forcing zone and partially reflected back. And the challenge here is that we have wave incidence into the forcing zone at many different incidence angles. And we will be interested in the reflection coefficient of this problem, especially called CR2D in the following. And the topic of this presentation will be to determine CR2D analytically. And the key question with this decomposition is perhaps the 1D theory, so for the long-crested wave propagation, sufficient to optimize the forcing zone? That is CR2D probably always smaller than CR1D or not substantially bigger? How come this question? At the last SNH, we presented such results, as you see on the left plot, with strongly reflecting bodies in free surface waves. And we found, or it appeared, that the reflection coefficient indeed corresponds very well to the one computed from 1D theory. We did not measure reflection coefficients there, but the optimum setting from 1D theory provided the best results. So let's have a look at the analytical solutions in the following. First, a quick overview of how the derivation of the 1D theory looks. We look at long-crested waves that enter the forcing zone, so shown in the upper right corner. This we can describe by a wave equation for the velocity stream function, and the term on the right-hand side is the forcing zone. This is equivalent to what we've seen before. Now, to have a solution that holds for all possible blending functions, I chose the approach to discretize the blending function from the continuous blending to a stepwise blending, so a piecewise linear blending. Then we have the following wave number for each segment, and wave reflection can occur throughout the forcing zone at each step. And actually, wave reflection will occur throughout the whole forcing zone, but we could show analytically that already a small number of steps, like 20 steps in this function, provides basically the same result as the continuous blending function, which also explains why in flow simulations, forcing zones generally behave indifferent to the grid that is used. So, taking into account the partial wave reflection that may occur throughout the zone, the solution for the stream function can be derived as follows. I won't go into detail into this. It is mainly a part of the generated right-going wave that decreases in amplitude, and a part for the reflected left-going wave. And if we now say that the stream function and velocity should be continuous over the whole forcing zone, then one can derive the reflection coefficient as follows. So this is the basic idea behind the 1D theory. Now it becomes interesting. We want to know for oblique wave incidence, how can we predict the reflection coefficient? For this, let us consider the following wave. So the black line here between points E and E dot is a wave crest, and this travels towards a forcing zone. Here, only the first two segments of the forcing zone are shown, shaded in gray. And if we follow the wave crest segment close to point E, the wave will travel to the forcing zone and then be partially transmitted and partially reflected. And now, to obtain a solution for this problem, we can actually, although the problem is two-dimensional, trace it back to the 1D theory if we make two modifications. The first one is that we take into account that the wave travels a larger distance through the forcing zone, which feels like an increased forcing zone thickness. And the second one is that we have a phase shift between interfering partial wave reflections. I mean by this that if we follow the transmitted wave, and this is reflected again, then this one will not interfere with the previous reflected wave because their parts are not aligned. Now, and this is why I added the point E dot. And if we follow the wave crest segment from there, then it will be at the second zone segment, partially transmitted and partially reflected. And then these two wave parts will be aligned, these partial wave reflections, and they can then interfere destructively. And so, since the point E dot is closer to the forcing zone than the point E, we get a phase shift theta. And if we take this into account, we can use the 1D theory with these modifications and arrive at a solution that looks basically the same as before, only that in the beta j+1 term, we have the phase shift theta and the increased forcing zone thickness. And thus, we can compute the reflection coefficient for any wave incidence angle theta. So let us now use the theory for a generic test case. We have a quadratic domain with side lengths d. Circular waves are generated at the domain center. The forcing zone with thickness xd is used for wave damping near all vertical domain boundaries. And the problem is symmetrical, so it suffices to look at the green triangle. Then the overall reflection coefficient at first sight can be computed as the integral over all wave incidence angles of the local reflection coefficient for a given angle. One has to take and this can be computed from 2D theory as we've seen before, but you have to take into account that for some angles, the waves will pass through two forcing zones. That is, for example, here, the wave enters the first forcing zone, passes fully through it, is partially absorbed and partially reflected, then enters a second forcing zone, is again absorbed partially, and then partially reflected before it leaves the yellow square. And in this case, the reflection coefficient actually is the multiplication of both reflection coefficients for each forcing zone. And this is always smaller than CR theta alone. And if we take this into account and select suitable ranges of angle theta, we can derive an analytical upper and lower limit for the overall reflection coefficient for this generic test case CR2D. And let's look at some analytical results for this test case. In the following plots, I will show where the upper limit for the reflection coefficient CR2D, so for our generic test case, where it exceeds the 1D theory prediction CR1D. Here we see results for probably the smallest domain size that one might use in engineering practice. It is only 3 wavelengths wide. On the vertical left axis, we see the forcing zone thickness non-dimensionalized by the wavelengths, starting from half a wavelength in the bottom left corner up to 2 wavelengths in the top left corner. On the bottom axis, we see the source term magnitude non-dimensionalized by the wave period, starting from low source terms in the bottom left corner to very high source terms in the bottom right corner. And in color, we see where CR2D exceeds the 1D theory prediction and by how many percent or by how much. And this is the results for the small domain. For a rather large domain, we see here the results. And basically, one can already see that reflection rarely exceeds the 1D theory prediction. And at most, 3% roughly in the small domain or 1% in the large domain. So very little. But these are the values for all possible source term strengths. So even some that don't make sense because they are very ineffective. So let's look what happens when the forcing zone is optimized based on the 1D theory. Here we see results for 2 different blending functions, linear and quadratic blending. We see the maximum of CR2D minus CR1D. So how much the reflection coefficient for our generic test case might exceed the 1D theory prediction. And the curves are here for different domain sizes, and on the bottom axis we see the forcing zone thickness in terms of the wavelengths. And we see that if the forcing zone thickness is 1 wavelength or larger, then the reflection coefficient will exceed the 1D theory prediction at most by 2%. And if we make the forcing zone just a little bit thicker, like 1.2 wavelengths, then the reflection actually will exceed the 1D theory prediction at most by 1%, typically much less, if at all. And if you're more interested in how the shape of these curves comes about, I can say more about this later on in the question section. Anyway, this held for all investigated blending functions in the study, so like linear, exponential, cosine squared functions. So we can, with good confidence, say that in practice, the 1D theory should typically suffice for optimizing the forcing zone, also for complex 3D flow simulations. Now let's look at validation. And first, I want to present to you some hydroacoustic flow simulations. Why hydroacoustic? Because the theory holds for various wave propagation mediums, so also for sound waves underwater. And since sound waves are a computationally efficient model of shallow water waves, since there's no dispersion, and 1D wave propagation, for example, is only a 1D flow, in contrast to free surface waves where it would be a 2D flow, this is computationally very efficient. And I use as a simulation setup basically the generic test case that we've looked at before. Here are results for the pressure in the domain after the simulation on the left for full wave reflection, so 2 small source terms, and on the right-hand side for optimum wave damping. There's a circular wave source in the center of the domain that generates a wave train, a short wave train, and the domain is very large, as you see, 38 wavelengths. And I investigated both linear wave trains and nonlinear wave trains. As you've seen here, the nonlinear wave trains are a sawtooth wave. And this, of course, is so nonlinear that it deforms as it propagates. And this is how it looks. You see the pressure over wave propagating distance. The finite volume-based flow solver Siemens star CSIM Plus is used in all simulations in the following with second-order approximations. So, and if we look at the results for the reflection coefficient, we find that they lie mostly within the theoretical upper and lower limits. Here for the linear waves, on the left axis, we see the reflection coefficient. So 1 would be perfect wave reflection, that's very bad, and we want to have the reflection coefficient as small as possible. On the bottom axis, we see the forcing strength, so the source term magnitude. The boxes are the simulation results. The red and blue lines are the upper and lower limit from 2D theory, as we've seen before. We also see the black line, that's the 1D theory, and we see this gives a decent upper limit of the actual reflection coefficient. Now, the interesting thing is what happens for nonlinear waves, and these waves are really highly nonlinear. That's the plot, and you see the differences are very, very small. In fact, for close to optimum tuning, no results are more than 0.2% outside the analytical limits. So we can conclude that the theory predictions apply regardless of wave nonlinearity. And the question now is why? Because the theory is derived, so this is not a restriction, but I only derived it using linear wave theory. And it's a very simple theory. So how can this give such a good prediction of the reflection coefficient for highly nonlinear waves? And to understand this, we have to understand the mechanisms, how forcing zones reduce undesired wave reflections. Say we have here a generated wave, a free surface wave that travels to the right into a forcing zone. See here the surface elevation of a wave propagating distance. The forcing zone is shaded gray. And thus we see the wave envelope gradually decreases within the forcing zone and there are no visible reflections. Now, the first mechanism is, of course, wave absorption. Some energy of the wave is absorbed within the forcing zone. However, this is not the only mechanism because it would not explain why for large source terms, where absorption should be high, reflection increases. So the second mechanism is partial wave reflections occurring throughout the forcing zone. And if the forcing zone is optimized, then it will always look as in the plot above. And the partial wave reflections will occur evenly throughout the forcing zone with very low amplitude. So this means the waves are basically linear. And the third mechanism is destructive interference, because all these partial wave reflections have different phase, and this can only decrease the amplitude of the reflected wave in the end. And if it is correctly optimized, there will be basically no wave reflection. So we can sum up that forcing zones have the singular ability to split nonlinear waves into many linear waves, or basically linear waves. And thus they behave similarly regardless of the wave nonlinearity and can be well predicted. And this is in contrast to boundary-based wave absorption approaches, and where you have that the reflection coefficient basically increases unpredictably with flow nonlinearity. And for complex flows, you basically cannot predict how much wave will be reflected. So this is the main advantage of forcing zones over other types of approaches, such as absorbing boundary conditions or active wave absorption. So to sum up, the theory that I presented for forcing zones applies regardless of the wave nonlinearity. So there's only a 1% or so where this can vary sometimes. And if you're interested in the details of this, you find more in my PhD thesis that was published last year and is available online for download. And this is really the main finding of my work. So now we come to a validation via flow simulations with free surface waves. Finally, the setup is a pontoon in deep water, long crested waves with roughly 40% of the maximum steepness, so moderately nonlinear wave. And we look at simulations in a small domain, like the smallest domain that probably would be used in engineering practice, and in a large domain. Forcing zones are shown in shaded gray near all vertical domain boundaries. And here's a look at the computational grid. So the problem here is that it is impossible for such small domains to calculate the reflection coefficient. This is because to calculate the reflection coefficient, you have to evaluate it over a specific time and space interval that has to be selected as such that the reflected wave has fully established itself in the evaluation interval, but no re-reflection from other boundaries can have entered this evaluation interval. And for such domains as one would use in engineering practice, it is impossible to calculate the reflection coefficient, therefore. So we devised the coefficient of accumulated reflection as follows. You need a reference simulation where the wave reflections are properly minimized. For this, we take a large domain with a very thick forcing zone that is optimized, where one can be sure that reflections will be 1% or less. So, and then one takes the free surface elevation from this simulation and performs simulations, for example, with a small domain or a not optimally set up forcing zone. And then from the small domain simulation, from the surface elevation, we subtract the surface elevation from the reference simulation and calculate the potential energy for the remaining surface elevation and relate this to the potential energy in the reference simulation. And this is how the coefficient of accumulated reflection works. And this has to be evaluated at a suitable time. Here would be the time that the wave energy needs to travel once through the whole domain. This is, of course, an approximation, but especially for smaller reflection coefficients like 20% or less, this will give like 1 or 2% uncertainty, hopefully. And if we now plot the results, we find that, again, they lie within theoretical upper and lower limits. We see on the left a small domain with a thin forcing zone of only 1 wavelength thickness. On the right, we see a large domain with a thick forcing zone and better damping and 2 wavelengths forcing zone thickness. On the bottom axis, we see the source term magnitude, and on the vertical axis, we see the reflection coefficients. And the red crosses are the coefficients of accumulated reflection, so our estimate of the actual reflection coefficient. We see the red and blue curves. These are the theoretical upper and lower limits. And we see the black curve that's the one-dimensional theory prediction. And basically we can say that the coefficient of accumulated reflection exceeds the upper limit for reflection coefficient at most by 2.1%. So this is probably background noise because there's some uncertainty in its estimate of the reflection coefficient. But basically these results look very good. And one can say that the optimum values for the forcing zone, for the source to magnitude, for example, and for the shape of these curves are well predicted already by the 1D theory. So this is of course can be seen more like an upper limit of the actual reflection coefficient, but this suffices completely for optimizing forcing zones in complex 3D flow simulations. So to come to an end, we've seen that forcing zones contain case-dependent parameters and that these have to be optimized to minimize wave reflections at the boundaries. We've reviewed the 1D theory, which provides a decent estimate of the optimum parameters and the corresponding reflection coefficients for the forcing zones. And computer code to evaluate this theory is published as open source, and you find the link in the paper. We also devised a more accurate analytical approach to consider the 2D waves radiated from a body within the domain. We found that both the 1D and 2D theory apply regardless of the wave nonlinearity, basically. And for complex 3D flow simulations, we find that typically the 1D theory is sufficiently accurate. So the recommendations for engineering practice would be to optimize the forcing zone parameters via 1D theory and to use a slightly thicker forcing zone than theoretically necessary. So between 1 and 2 wavelengths, depending on what waves are studied and how sure you want to be about the reflection coefficient. So that's it from my side. Thank you very much for listening, and I'm looking forward to the questions. Thank you.